All right. Should I skip the introduction?
Yeah. I gave some good background.
Yeah. All right. So everybody knows what BPF is. You build a program, the kernel loads it, and then you can make it do stuff like trace code or filter packets. Rather than introducing the technology, this talk is more focused on integrating it in your applications, like a profiler or an endpoint agent, like osquery. We have looked at many tools and libraries when we decided to implement BPF support in osquery, but their primary use cases never really aligned too well with what we needed. The primary goal was to be able to programmatically generate the programs we needed at runtime, allowing developers reasonable freedom over the whole process. And this is how we implemented it. For this talk, we were looking for a project that wasn't too complex to write, but still worth the time spent on it for learning purposes. It is a C++ application that times how much it takes to service a system call of choice. Even though it is simple, it should illustrate all the basic concepts that are required when writing a more complex tracing solution in an actual product. These, I think, are the most important requirements for an ideal BPF integration. There are many interesting tools that can be easily redistributed because because they cannot be easily built and deployed. So those two requirements are easy to meet. We're going to use modern CMake and integrate a recent clang toolchain. This will allow us to build once and deploy the binaries everywhere. Another nice to have is the ability to compile everything to a single binary. We're going to use static libraries to achieve this. You should, of course, avoid calling other command line tools, because that would not be ideal. The most important requirement, however, is to allow users to configure what our BPF programs should do. This means that we'll have to generate the code ourselves, since we cannot reuse pre-built instructions. So this is how our simple application works. Once the program is started, it generates a pair of BPF probes for the chosen system call. The first program handles the enter event when the function is called. The second program handles the exit event when the function exits. Both programs are then loaded and attached to the two trace points, which are the event sources that will call our code. When the syscall is called, the enter program uses a BPF map to store its state data, which in our case is a simple timestamp. At some point in time, the syscall will return, calling our exit program. We retrieve our data from the map so that we can time the call. Once we have the result, we send it to the user mode application using the perf output. So I've mentioned maps, trace points, and perf outputs. Let's define them a little better. Maps are basically the bread and butter of BPF. They can be used as an alternative way to allocate memory and are really useful to keep state between different BPF programs. There are many types of them, but we are only going to use arrays and hash maps. They are useful also because they can be used both by the user code and the BPF code. Not much else to say here. They behave as you would expect from a key value store. While it is possible to use maps to communicate with the application, perf outputs are way better. Instead of having to work with values of a fixed size, with perf outputs, we have a ring buffer. Another good thing about them is that it is easy for the application to wait for new data without having to look for entries in a map. Trace points are the last building block in our project. They are what is actually calling our BPF programs. We are all interested in the syscalls category, but they all work the same. When tracing functions, as I mentioned, you will always have two. The enter trace points come with the function parameters, while the exit trace points carry the exit code. There are other ways to receive events like kprobes or uprobes, but the strength in the trace points is that they have a stable interface. The information they export, like the parameters, will not change easily. We are going to generate our BPF programs, so it is useful to take a brief look at the constraints we will be working under. There are many cool things happening with BPF, but as we all know, the major distributions are really slow to adopt the latest kernel. So kernel version 4.18 is a good version to target, as it is the one shipped in CentOS 8. Some of the constraints listed here loosened up in the more recent versions. So BPF programs are really only made of a single function. It is, however, possible to pass the execution to another program with some limitations. There is really no executable image format involved in a BPF program. The raw instructions are sent as they are to the kernel using a dedicated system call. The major downside is that there is no way to define constants like you would in a standard F program where a data section is available. So for example, if you want to use a string, you have to push the characters onto the stack. Jumps can only go forward, and this affects how loops are built because we have to enroll them. Additionally, given that we only have a limited amount of instructions, the code can only loop for as many times as the remaining code space we have allows for it. Code is verified before it is run. In general, if you always check your errors and initialize the memory, the program will never be rejected. The last limitation is that there is no way to allocate memory, and the stack is also very limited in space. It's not a huge issue if we use maps to provide buffers for us. BPF programs would not be really useful without a way to interact with the system. Probes are allowed to read from and write to maps and perf outputs. Memory, however, cannot be altered, and pointers must be read explicitly. It is also not possible to alter how system calls work. As a general rule, unless you're using kprobes with special kernel settings, you are never allowed write access. In order to perform these operations from within the probe code, the BPF VM defines a number of operations that are called helpers. Helpers are available to the BPF code by calling special addresses. This is a moving target, and depending on the kernel version in use, you will have more or less helpers. Luckily, the verifier knows about this and will reject your code if you try to use something that is not available on your current kernel. Importing a helper is easy. The bpf.h header contains the full signatures that you can use to define the function types. They are also identified by an enum value that you can use as a destination address when you want to call them. Sometimes you will see some special types. The most common ones are the context pointers or the struct maps. For context, you can just pass the entry point argument as it is. For the maps, there is a special operation you can use to convert file descriptors to the right type. Here's an example for the ktime getNS helper. You can see from the function type that we're not going to pass any parameter, and that we are expecting a 64-bit integer as a result. The call destination, as I mentioned, is the enum value found in the BPF header. So let's look at some code. Creating the BPF module is easy. You only need to care about setting the right triple and data layout. We can use a single module for all our programs, and it is actually encouraged. The advantage is that this will allow you to share types and functions between different BPF probes. The next step is to identify what kind of data we're going to work with. A special file in the system named format contains everything we need. Inside, you will find an ID that we'll need later on when configuring the event, and a list of fields we will be able to access from BPF. Here's the format for the open syscall. At the top, you can see the ID. Under Format, we have the common header for the syscalls, made of the first 5 fields. It is then followed by the syscall parameters if this is an enter tracepoint. If it is an exit tracepoint instead, it will only have the red code of the function. We can now create the parameter structures, one per BPF program. It is just a matter of reporting each one of the fields found in the format, and then call the factory method. If you are familiar with BCC, this argument is known as the CTX or context parameter, and ptregs if you're using a kprobe. As we don't use this data in our simple project, the companion code skips this part. At this point, we can create the functions. Since we are using a single module, we're going to ask LLVM to put each function in its own section. If we don't do this, we won't be able to easily split them from the single code section we will obtain. It is now time to start generating functions. We are now looking at the first one, handling the enter event. The enter function is rather easy and is only made of 3 main operations. The first one is to generate a suitable key for our map. We need something that the exit function can easily recreate to access the same element in the map. The process and thread IDs are usually a good option for this. The next operation acquires the current timestamp and will tell the exit program when this system call has started. Before we terminate the program, we store this value in the map. With the enter function ready, we need to build the exit one. The exit program is slightly more complex. We are acquiring a map key again in the same way as before. If we are still inside the same thread in the same process, this value will let us access what we have stored in the previous program. To read back the previous timestamp, we can use the lookup helper. This time, we have to check the return pointer and terminate the program early if it is not valid. This is important. If we do not do this, the verifier will reject our program and the load will fail. In the second part, we get the timestamp again and use it to determine how much time has passed since the enter event. The BPF perf output is then used to send this result back to the user mode application. Once the functions in our module have all been completed, we can compile the module. To do so, we first create the engine builder and set the target architecture to BPF. We have configured function so that they end up inside their own section. So we will use the section memory manager object to split the module into 2 different programs. We can now read the instructions back and load the programs. They are loaded with, again, the BPF system call. There is no glibc wrapper for it, so you will have to call it manually. The first thing to identify is to identify our program as a trace point, because it is what we will be using it with. Next, we pass the instruction bytes and count. The license is mandatory. You may not be able to access all the functionalities without the GPL license in there. You could, in theory, keep the generator closed source, dump the IR to disk, and mark it as GPL. We can also optionally pass a character buffer to get back some diagnostics. If the load has succeeded, we will get back a disassembly. If it fails, we will get the errors so we can debug it. We finally have our programs loaded, but they're not being run yet in any way because they're not attached to an event. So let's fix this. Creating a trace point is really simple, and we only need the trace point identifier, which can be found in the format file we have seen earlier. The perf event open is again not present in the glibc headers, so we will have to call it manually. We want to trace the system calls system-wide here, but this API will allow you to configure things a little bit and filter based on process ID or processor core. Once we have the event file descriptor, we can finally attach our program against it and enable the event. Once this happens, our probe will actually be called. We have used a perf output in the exit program, so let's see how it is set up from the user mode application. We first need to determine how many possible processors we can have on the system. This can differ from the amount of online usable processors that you can see from top. VMware Fusion, for example, we report 128 possible processors. Once we have this number, we can create the perf event array map with the right size. We then create a perf output, one per processor, and set the file descriptor inside the map. Next, we want to create a memory mapping for each one of them, where we can read from when there is new incoming data from our BPF programs. For reading, we have a couple of things to keep in mind. When calling the perf event output helper from the BPF code, it is possible to specify which output to use. Usually, the most common choice is to just pass -1 and let the program automatically use the output associated to the current processor. From the user mode application, you can use the poll system call to wait for data on all the file descriptors. When one of them is readable, you can read your data back from the right memory mapping. At the start of the memory mapping, we have a special header that we have to interact with when reading data. Two fields, data offset and data size, tell us where the data region starts and ends. We can then use the data head and data tail offsets to locate our buffer inside the data region. When trying to read new data, you have to keep in mind that the buffers could wrap around at the edge and continue at the start because it is a ring buffer. Once we have acquired our data, we update the data tail field to confirm perf that we have read this buffer. Failing to do so for whatever reason will cause perf to generate a warning when the new data will eventually wrap around and override what perf thinks was unread. That is all. Hope you enjoyed my talk. We have published the companion code on our GitHub. And of course, we are on Slack if you need us. I would like to point out this great article from William that you just see earlier about the get element PTR.
Hey, Alessandro, great overview of a very low-level perspective on top of eBPF. A couple of questions, though. So this opportunity that you've used to rethink how to use BPF inside of tools like osquery, what does the alternate path look like, and why is this better?
So we have approached a couple of different paths with osquery initially. So the first one was to use BCC, which is a great way to use BPF. However,
so how does BCC work, though? I don't pretend I'm not familiar with it. What does it do that's so constraining?
So the issue we had with BCC is that it will force you to write a lot of boilerplate code to handle things. There is nothing wrong with using it per se. It's a great product. However, you really have to define in the BCC language what you want to accomplish. In our case, we don't care about each different behavior of each system call we need to handle. We have written a library named eBPF pub that will automatically handle everything needed to capture a function call based on a prototype. And will handle things like capturing parameters by value or by pointer. And you can define whether this should be captured when the function is called, when it should exit. And you can also use size fields And these things usually needs to be handled manually with BCC.
Okay.
While
So
with
from my like naive perspective, so the BPF thing, you're basically taking these tiny little programs that have really serious constraints about how they can be written, and you're launching them into space, into the kernel to be executed and run really quick and gather a bunch of data and give it back to you. Is that like a naive way to describe eBPF?
Yeah,
Yeah.
that's actually a great way to describe it.
So the BCC library basically has just a whole bunch of stock capabilities that it can use. It's got these really like static precompiled, like, do you want to do A, B, or C? Pick one, right?
You actually have a way to do a lot of things, but you will have to code the things manually.
Okay.
And the alternative, I mean, re-implementing what we did in BCC means that you will have to splice and patch together strings of C source that you try to generate on the fly. And BCC also injects a lot of things inside this program that is then compiled to BPF.
Mm-hmm.
And it eats up quite a lot of instruction space. So if you were, I mentioned that you only have a limited amount of instructions.
Okay.
In our test with BCC, we were only able to capture close to maybe 11 parameters of the execve system call when trying to capture the argv parameters. With our library, which is a lot more constrained and lightweight, we can capture 14.
Okay, so BCC has these kind of kludgy building blocks that you can try to use, and you're constrained by, it's got like the worst of both worlds because the building blocks are written in C, and the building blocks come with a bunch of extra weight, and because you're shoving these tiny little mini programs into the Linux kernel, you want them to be really efficient, and it's still difficult to do that because the BCC stuff just like comes with out of the box, like here's what you get, you can't modify a whole lot. And then the difference with your approach is that these little programs are dynamically created to use the minimal resources that they require. Is that the comparison?
Yeah.
Okay. Do you
So
have...
the eBPF pub library is focused on the developer, where usually you don't want to script it. You just point it against a function, whether it is a function on disk, on a user mode binary or a syscall, and you tell it, give me everything. So you just define a prototype. If it is a syscall, it is already known by the library. You just point it against it, and it will return everything. You only have to care about processing the arguments.
Gotcha. So the really easy way to boil this down is that the BCC approach is for the naive operator that doesn't want to master the low-level details of BPF, but just wants to take advantage of the functionality. And your approach with the library is more the developer approach, where you do understand a little bit about what's going on and want to interact with it more directly. And by doing so, you can be more efficient, you can be faster, you can create smaller programs, and you can integrate it into whatever you're building. That's the difference, right?
Yeah.
Gotcha. Okay. Do you have any like comparison kind of like what are some things that you've been able to do with your library-driven approach that would have been really difficult to do with BCC?
So the major issue with BCC is that it is really hard to redistribute things. With osquery, we were able to easily implement a full publisher and also still have a single binary that pretty much has no dependencies. And it is also way easier to maintain on the osquery side. With BCC, you can, I believe that BCC is a great way to debug things because you can use the power of Python and the libclang parser to parse kernel headers and dump kernel structures in real time. But it was causing some maintenance issues and developer issues on the osquery side. And that is why we ended up building our own solution, which is, it is maybe more, it is of course less powerful than BCC because BCC has a full scripting language where on our side we have a tiny DSL to describe just the prototypes. But that is exactly what we needed for osquery.
Great.
And for many other monitoring tools.
So now, what is the status of this in osquery? So we developed this as a prototype. We've got it all fully featured out here that you've described with this presentation. But clearly, the most important thing is that it gets into people's hands. So if you're running osquery right now, are you using this code?
Only if you use master, but the next release will contain it.
Okay.
And we were also able to integrate this into the product of some of our customers.
Right. Yes, we've been doing lots of endpoint security, proprietary patch-ups. Okay. Now this all makes sense to the pointy-haired boss. Anybody have questions for Alessandro?